Hello everyone, welcome to this video. In this video I'm going to walk you through the simulation that I made in Python using the neat and pygame libraries. This project was inspired by the Bibbit simulation and also by the video of Tech with Tim, which showed how to use the neat library with pygame. In this simulation we see a surface in which there are green circles which represent the food and the blue things which I have called organisms. The goal of the organism is to survive for as long as possible, and they do that by eating the food they see. Eating food makes them gain energy, while moving forward drains their energy. And oh, each frame their energy is also decreased by some amount, cause fuck them. Here in the corner you can also see their energy statistics, as well as their angle and health. Now, how do these organisms know how to move left or right? This is not hard-coded, as the organisms are controlled by a neural network, which is random at the beginning but evolves over time each generation. When I pause the simulation, we can take a closer look at the neural network of each organism. I will click on Draw Neural Network and show the node names. As you can see, the organisms have 2 input nodes and 3 output nodes. And between those nodes there are weights or edges, where red represents a positive weight and green a negative weight. Cause I'm built different.
What?
Nah, I'm joking. I'm a good boy. The green edges are positive and the red ones are negative. So one of the input nodes is the angle difference. And if an organism is facing this way, the angle difference is negative. And if it faces the other way, the angle difference is positive. A good performing organism who wants to reach their food wants to have their angle difference to be as small as possible. The decision is made by calculating the product of the input and the weight. If the product is larger than some amount, the output will be activated. So for example, the input node value is -10 and the activation threshold is 100. If this edge has a positive weight of 10, then the product will be lower than the activation threshold, and so it will not move to the right. However, if the weight is -11, then the product is larger and it will move to the right, which is what we want. Now, as I said earlier, all those numbers that I mentioned are completely random, but some organisms by chance got good numbers, which resulted in a good performing neural network and an organisms that can find their food efficiently. Now, what neat does, from this whole population, it takes the organisms that perform the best and combines those neural networks into an adjusted network. Now, this newly created neural network could be better or worse, but the thing is, every generation only the best performing organisms are selected, and as a result, the organisms generally perform better over time. So that was my quick, not so quick TED talk about neural networks. This was a rough explanation and there's many more to it. And if there was something wrong, please correct me. So anyway, back to the simulation. When all organisms have died, the best performing organisms are selected and bred to create the new population for the next generation. And here in the lower left corner you can see which generation is currently running. Besides the evolving neural network, I also wanted to add some physical traits. As far as I'm aware, Neat doesn't have an interface for adding physical traits, and because I don't know how to do this in a good way, I might have or might have not changed the library code by adding a few lines. Yeah, that should work. Now that I have the parents key, I can use that to access the physical traits of the parents and combine those to create the physical trait of the newly bred organism. The physical traits that can be evolved are the size, the speed and their vision. Bigger size makes them have a higher health stat and a higher collision radius for eating food, but on the other side, their costs of living goes up, making them lose more energy each frame. A similar thing goes for speed. Then I also make the trade-off for vision, where a wider vision angle results in a lower detection radius, while a more narrow vision angle gives them a higher detection radius. And the detection radius is kept because otherwise my laptop is preparing to go to the moon. Evolution in real life and also evolution implemented in this simulation tries to find a balance between the trade-offs, which is really interesting to see. That's most of the important stuff of this simulation, and then I also made some extra features. such as turning on and off the vision lines, and also zooming in and out of the map. We can also select organisms by clicking on them to see their statistics. The next ideas that I want to implement, which I'm probably not going to do because I'm lazy, are adding predation and some kind of biomes. I really want to add the latter because I think that changing environments are the drive for evolution and speciation. So yeah, let me know what you think about this project in the comments down below, and I'll be happily reading them. Thank you all for watching, and maybe till next time. Bye bye!